Okay, so to start Unit 4, we're going to start talking about types of bonds because this whole unit is about writing the names and formulas of different types of compounds, and each type has its own rules. So the first thing we've got to be able to do is tell the difference between them. And page 1 of our packet is going to start with some super duper basics, and page 2 is where we're going to do most of our writing. Then we'll finish up with just a little bit on page 3, kind of applying some of the stuff from page 2 in order to answer some questions. So page 1 starts off pretty general. Like I said, what is a bond? Why do we form bonds? Well, bonds are just the attractions between different atoms, and bonds form to reduce the potential energy of that system of atoms. Really, when it comes down to it, it's kind of a physicsy perspective about reducing energy. We've talked about the octet rule. Every atom wants 8 valence electrons to get more stable. That's their low energy state. And so they're either going to gain electrons or lose electrons or share electrons in order to get more stable. And it really comes back to electronegativity at the basic level, but we're not going to need to have memorized electronegativity values or even look at a table of values and do some calculations about the electronegativity difference between our elements, which is technically how our different types of bonds are different from each other. We're going to kind of simplify this down because the electronegativity is greater for our nonmetals than our metals. When we look at these different types of compounds, we can kind of generalize this down to the types of elements taking part in our bond. So remember the left, kind of below the staircase, all the way on over to the very first column. Everything except for hydrogen over here is a metal, and then our non-metals are just this top, kind of to the right above that staircase there. And so the most general way to tell when something is going to be an ionic bond is when you have a metal and a nonmetal. They do technically have the largest electronegativity difference because we got some high electronegativity values getting with some lower electronegativity values. They're different types of elements. They have the biggest difference in their electronegativity, which we call ionic. And they're ions there because if you remember, electronegativity is the strength of our atom in a chemical bond, kind of how hard they can pull on the electrons in the bond. What we're doing is combining a strong element and a weak element. And so the strong element is going to steal the electron from the weak element. It's going to transfer, we'll write that on the next page later, it's going to transfer the electron from the weak to the strong element. And they're not going back, and that means that they're going to be ions. They're going to have charges there in that compound. Then if we have nonmetals only forming our compound, that's covalent compound. And technically there are 2 different types of covalent. We'll get into that difference and how to tell polar from nonpolar next unit. But just keep in mind there are different types of covalent compounds, but they're all always made up of nonmetals only. The difference between them comes down to the electronegativity difference. If it's practically 0, or if there is a little bit of a difference, just not enough of a difference to steal the electrons, like what we see in ionic. Because the electronegativity of these nonmetals is so close to each other, they have smaller differences or no difference, they have to share their electrons because both elements are equally strong. So they're pulling on those on those electrons in the bond. They're both strong, so they can't steal them completely. They just have to share. So some quick notes before we go on to the next page, just in general. You'll notice that I drew this arrow here at the top because this is a spectrum. We're not just completely ionic or completely covalent. We do have something in between. We call polar covalent, but we can also be between polar covalent and ionic. We're not just 100% ionic or covalent. Lots of bonds, lots of compounds have some character of both, and it just kind of depends where on the spectrum they are. And it is very rare to have a molecule that has exactly 0 electronegativity difference. That would have to mean that that's an atom bonded to another atom of the same type, 2 identical elements. And that doesn't happen much. There's actually only 7 elements that do that. We're going to talk about them in our next chunk of notes. They're called diatomics. So at the top of the next page, we start to discuss these different types of bonds that can form, ionic, covalent, and we're also adding in metallic here. It's not its own type of compound. We're not going to be writing metal names because they're technically mixtures, not compounds, but they do have metallic bonds between metal atoms holding them together, whether it's a single element of a metal or different elements combined together. They all have metallic bonding. Anytime you got more than two metal atoms together, they're going to have a metallic bond holding them together. And I've already kind of inferred and implied the difference between these is about how their electrons are treated depending on those electronegativity difference. Those ionic compounds, because they have such a big electronegativity difference, the strong one and the weak one, the electrons are transferred from the metal to the non-metal. We're in fact going to be drawing these structures, drawing arrows showing that movement, showing that transfer from the weak element to the strong element. Then in covalent, since they're both equally strong, they're going to be sharing the electrons. And I know this is a little small. You don't have to draw this diagram, but I basically have two atoms here represented by these two big circles. And then the two small circles are their electrons, and they're being shared. They're still left between them. That dotted line is just trying to show the bond. We generally represent bonds as lines there. And like I said, we'll get into what's different about polar and nonpolar covalent next unit. But nonpolar is where they share equally. This polar covalent example here, I have those same two atoms. If I could draw, they would be the same. But here my electrons are closer to one than the other. So one of my atoms is stronger, has a stronger pull, but not strong enough to completely steal the electrons. They're still being shared between those nonmetals, just maybe not shared perfectly equally. And then our metallic bonds, a lot of people think, oh, those are shared too when they see this description. The sea of electrons kind of shared between the metals. It's almost hard to say that without saying the word share, but this sea of electrons is more than just sharing. It's a big, what we call delocalized sea of electrons. It's just all of these different atoms here in the big circles that you see are all in this kind of lattice, in this arrangement, and then their electrons just kind of wander in between all of these atoms. They're not stuck around one specific atom. They're delocalized. They can wander wherever. This is a little bit more like a potluck than just sharing. Like if you shared your lunch with a friend, then maybe like you give him half of your sandwich and he gives you half of his sandwich. You shared. But in a metallic bond, it's not just a one-to-one sharing. This is like a potluck. Everyone brings their own food, puts it in the middle of the table, and then the food has become everyone's food. You don't just control it and pass it out. Everyone just gets what they need from the middle of the table. So it's similar types of sharing, but if you think about it, that type of potluck you only have with your strongest bonded people, your family or your really close friends, because you can't just trust any old person, any random stranger, just, hey, we're having a potluck on Friday, bring something. Like, you don't know if they're bringing something, you can't even hold them accountable to that. So it's really kind of a stronger bond than just the normal sharing in general. And as we'd already implied on that other page, but here we have it again, ionic bonds are between a metal and a nonmetal. Covalent is between two or more nonmetals. And then as the name implies, metallic are just between metal atoms. And I am going to have you write down a couple examples. I know you're not necessarily going to understand where all of these numbers come from in these different formulas, but you're welcome to ask. We can talk about them, or you're going to learn about where exactly these numbers come from as we move through this unit. But they are important, and it is important that there's subscripts down there, all except for this SO4 minus 2. That minus 2 is a superscript, showing that that group of atoms has a charge. Just notice that all of these ionic compounds are a metal and a nonmetal. In fact, the metal is first, nonmetal is second, just like I wrote that in our notes. Our covalent is all nonmetals, whether it's a single nonmetal or sets of nonmetals together. It's only nonmetals. And then our metals are just metals only. Feel free to pause if you need to finish writing some of this down. This next page has a lot of writing on it, and the first and the third thing in this space are required. You need to know this. The middle thing is really just going to help you understand the first thing. It's not something I'm going to test you over. So if you don't have the time or you don't want to write down all of that, then you can skip over the middle kind of section of each of these bond descriptions. So we're going to talk about bond strength, the strength of all of these different types of bonds. The first thing I want you to understand is that they're all measured different ways. We can't test their strength the exact same way because they're not put together the same way. And because of that, it actually makes it kind of hard to compare the strength of an ionic bond to a covalent bond. Not only are there thousands, if not millions, of different ionic compounds that are all, slightly different strengths, but since the way we measure their strength is different, it's hard to compare. It's like comparing apples to oranges. They're just different. So we are going to, by the bottom, that last bullet is going to compare the strengths of these different bonds, but it is kind of hard to, because ionic bonds, we're measuring the lattice energy, covalent, it's the bond energy, and for metallic bonds, it's the heat of fusion. And these are all different. And that's what this second bullet point is, as well. What are all of those fancy words? So I've just defined each of those bold terms in that first bullet. Once again, this is not something that I am going to put on a test. You do not need to memorize these definitions. But lattice energy is the idea that these ionic compounds are in this kind of regular arranged structure called a lattice, and that puts our ions, our different charged atoms, close to each other, and the level of attraction between those ions is the measure of the lattice energy, how close and how strongly that lattice is held together. And the lower lattice energy is actually more stable. Once you get to physics, you'll learn that those negative energies are actually more stable, more attracted to each other. On the other hand, covalent bonds with that bond energy is a little bit more kind of straightforward. It's literally the amount of energy to separate the atoms. If we tried to pull two atoms apart, how much energy do we need to pull them apart? And that is more stable when we have high bond energies, because if it takes a lot of energy to pull them apart, that must mean they like being together. And the heat of fusion is the energy required to turn solids into liquids. And once again, high values are more stable, because if it takes us more energy to make it into a liquid, to get those atoms separate and moving, then that means that they were more stable as that solid state. So if we were to compare the strength of these different bonds, and that's what I just kind of added this last bullet point down there, the comparative strength, then both ionic and metallic tend to be very strong, we'll call them strong bonds. Like I mentioned earlier, there's a wide range. There's lots of different ionic compounds, and some of them are stronger than others. There's lots of different metals. Some of them are stronger than others. But especially when compared to covalent, ionic and metallic are so much stronger than covalent. Now, covalent also has a pretty wide range of compounds with different strengths, but they are always going to be not always. Things like diamonds, that is covalently bonded, but they are a lot stronger than a lot of ionic and metals. So there's always exceptions to the rule, but they tend to be lower energy, lower stability than our ionic and our metallic. But it is hard to compare because they're all measured in different ways. So if we take those bond strengths, we can interpret some of the melting point and boiling points. And you can probably think this through already on your own. If I have a strong bond, like an ionic bond is very strong, is it going to take more heat, more energy to separate those molecules, or less? Well, hopefully you can understand that it would take more energy to separate a bond that is being held together strongly. So our strong bonds, ionic and metallic, tend to have high melting points. Covalent bonds have low melting points. They will melt at lower temperatures. Same with the boiling points. High for our ionic and metallic, low for covalent, which means at room temperature. We think about our high melting points. That means at a high temperature, they're going to melt. So at room temperature, they're not going to be melted yet, which means they tend to be solids. Now, of course, our covalent is a wide range, so we could have some solids, some liquid, and some gas. It really depends on the specific elements and compound that's being formed. Metals do tend to be solids. There are two exceptions. Mercury is a liquid at room temperature, and gallium it depends on how warm your room is, really. Because in like my classroom, which tends to be a little bit cooler, it'd definitely be a solid, but if you just held it in your hand, it would melt. So it melts at a very low temperature, just not quite room temperature all the time. So the last two things on this page, before we go answer those quick couple of questions on the next page, is about solubility and conductivity. And before we even get to the answers, I need you to make sure that you know what these words mean. Solubility measures or compares if something will dissolve or how much of it will dissolve. So here we're just going to be putting a yes or a no for will it dissolve. Now, there are actually two different types of conductivity: thermal, which is heat being conducted, or electrical. And we're talking about electrical conductivity here. And in general, I know you haven't learned a lot about electricity, but electricity is just electrons flowing through a substance. So when we're asking, will it conduct electricity, we're really asking, will it let electrons flow through it? So in terms of our solubility, ionic compounds, yes, should be soluble in water. I do want to add that little note that it's most of them will, because come Unit 10, I'm going to rock your world and show you how some ionic compounds just don't dissolve. And we can predict whether they're soluble or not, but we're not quite at that level. So at this point, we should assume and expect ionic compounds to dissolve. Covalent compounds, it depends on whether they're polar or nonpolar. Nonpolar are no fun. They don't dissolve. Polar do. And then metals do not dissolve. They will react with water. That does not count as dissolving. And with electricity, hopefully you know that metals conduct electricity pretty well. That's one of their main properties. But ionic and covalent is kind of wishy-washy. Ionic is the most complicated because it depends on their state of matter. As a solid, they do not. As a liquid, if we melt them, then they do. Or if we take that solid and put it in water, turn it into a solution, then they do conduct electricity. For covalent, just like with solubility, nonpolar, no fun, does not conduct. Polar sometimes does, only if it's aqueous, meaning dissolved in water. And then metals, like I already said, do conduct electricity. So, on top of the next page, and this is the end of this chunk of notes, we're going to kind of use those properties to discuss some other general observable properties and kind of use what we know about these bonds to predict some of their properties and explain some of the properties that we see. And before we even get into the answers, kind of like with those last two rows on the last page, I want you to define these two words to make sure you know what they are. When we answer the question, why are metals malleable? Well, what is malleable? It just means bendable. And kind of the opposite of malleable is brittle. So in the second question, we're going to talk about why ionic compounds are brittle, which means they are not bendable. They shatter if you try and bend them instead of actually just bending. So malleable, you try and change the shape, it changes just fine, and it just bends into that new shape. With ionic compounds, you try and bend it, and it's going to break apart into a lot of itty-bitty little pieces. So why are metals malleable? Well, it comes back to their electrons. Remember that sea of electrons, the big wishy-washy area the electrons just flow around in? Because they can move and flow freely, we can move those atoms around and the electrons just flow and move with them and take up their new space in the new shape that you've mushed the metal into. Ionic compounds, on the other hand, have that lattice that we talked about earlier, with that lattice energy. That means that those positives and negatives have to be very specifically aligned. And this is an image of an ionic lattice. You'll notice every single negative has a positive on either side of it. Even in the very middle, we've got a negative with positives on every single side of it. There is no negative next to another negative because opposite charges attract. That's what holds this ionic compound together. So we line up as many positives and negatives next to those opposite charges as possible. If I just tap an ionic compound the wrong way, and think of like a glass, you just put it down wrong on the table. You didn't mean to break it, but you just put it down a little too hard, or on like a small, something is on the tabletop, and when you put it down, it just misaligns that ionic lattice by one atom. And remember, an atom is really, really small, so it might not even be visible, the little dent that you've put in it, the little misalignment that's happened. But as soon as we get this shifted, so that we have a negative charge now next to a negative, a positive next to a positive, just shifting this down by one atom thickness, we have things with like charges next to each other, and like charges repel. So that ionic compound will literally break itself apart, push itself apart, and shatter into a million little pieces, even when you just barely tapped it. And you're like, I didn't hit it that hard. It shouldn't have broken. Well, you hit it just hard enough to move a single atom, or a single row of that lattice, and the lattice energy did the rest. We've kind of already talked about these next two. Why are ionic compounds solid? Well, that's about their bond strength. Because they're such strong bonds, They're held together by more energy, so it takes a lot of energy to separate them. Why do our molten ionic compounds conduct electricity? Well, when they're molten, when those ionic compounds are liquid, the atoms and molecules can flow and move, which means that they can carry electrons, have those electrons flowing, which is all we need for electricity to be conducted. So that's our notes about our properties and types of bonds, and there is a little GimKit game that goes along with this that you can play to practice using these properties to classify your substances, but also just looking at formulas and names and classifying things as ionic, covalent, or metallic. It's important steps, because remember, everything after this, we need to know what type of compound we're dealing with so we can follow the right rules to write their names and formulas correctly.